Hi everyone, I'm Hongbin from Duke University. Today I'm glad to present our recent work called Mudjacking, Patching Backdoor Vulnerabilities in Foundation Models. Foundation model has become the cornerstone of artificial general intelligence. So given a large amount of unreliable data publicly available on the internet in multiple modalities, we can use self-supervised learning to pre-train a foundation model, which is a neural network, serve as a general-purpose feature extractor for various intelligent downstream applications, including classifications and also a lot of generative AI applications. And there are many popular foundation models like GPT, Clip, and Segment Anything may be well known to a lot of audience. So our paper, Mudjacking, aims to patch the backdoor vulnerabilities in such foundation models. And throughout the presentation, I will use the classification for simple illustration. And our method can also be generalized to other generative AI applications as well. So how to use a pre-trained foundation model to build a downstream classifier? Given a set of training inputs of downstream tasks, we can use the foundation model to extract feature vector for each of them. And then together with the corresponding levels, we can build a downstream classifier using standard supervised learning. During testing time, given a testing input, we can use a downstream foundation model to extract feature vector for it, and then use a trained downstream classifier to make the final prediction. So how can backdoor vulnerability happens in real-world foundation models? Because they collect, foundation model provider, they collect a large amount of pre-trained data from the public internet. And there are some poisoned, maybe some poisoned backdoor data can inject backdoor into pre-trained foundation models. And such backdoor foundation model will impact all its downstream applications. So to be specific, backdoor downstream classifier will not impact like the prediction for clean images. But as long as the images was embedded with a white patch trigger here, which is a backdoor trigger, it will misclassify as attacker desired. And such backdoor foundation model will provide backdoor feature vector for other downstream applications. So it will impact other classifiers as long as the backdoor trigger exists. So we denoted the backdoor trigger as TB here. And we want to say backdoor vulnerability leads to a single point of failure in the whole AI ecosystem, including a lot of downstream applications. So in our system setup for the patching, we consider a foundation model provider like OpenAI pre-train a foundation model and then serve the foundation model to different downstream clients to build downstream intelligent applications. And during the deployment of downstream intelligent applications, it may find a pair of inputs consisting of a misclassified input and a reference input, which both are planned to human beings. But the model will make different predictions for them in the downstream application. So we call this pair of input as bug instance. And note that the misclassified input contains the backdoor trigger here. So after receiving the backdoor reported bug instance, basically means the backdoor has been detected and also the foundation model was backdoored. A foundation model provider can use our method to patch the foundation model to obtain a new one that are free of backdoor. In terms of the goals for patching, we formulate backdoor foundation model as H and downstream classifier as F. A naive way to patching backdoor vulnerability is to patch downstream classifier alone. And in our experiments, we show it's insufficient, and more results can be found in our paper. So our solution is to patch the foundation models so that it can patch the backdoor for millions of downstream applications. And we have 3 patching goals. The first one is called effectiveness. So basically, after patching, the patched downstream classifier built on top of the patched foundation model should make the correct prediction for the backdoor input. The second goal is locality of the patching. We do not want the foundation model to change its feature vector for a lot of other clean images because it's a general purpose feature extractor. It's not only used for one instance. So we want for any clean input X, we hope the patched foundation model output similar feature vector together with similar to the original backdoor foundation model for clean input. The third goal is called generalizability of the patching. Basically, we will not only patching like effectiveness goal, we only patch the prediction for the feature vector for the backdoor image. But for any clean images embedded with a trigger, we do want the patched foundation model to output the feature vector as if the trigger does not exist. So formally, we formulate an optimization problem with 3 objective functions for 3 patching goals. The first one is effectiveness loss. Basically compute the cosine similarity between the embedding vector of the backdoor input and the reference input. And the second loss is the locality loss. Given a certain amount of validation data, we can use it to mimic the distribution of clean input. And we hope the embedding vector of the patch foundation model to be similar as the original foundation model for clean input. The third goal is generalizability loss. We also use the validation data. So when we embed it with the reverse engineered trigger here, it will output similar feature vector as if the trigger does not exist. And we formulate a weighted loss for the for all these 3 patching losses. And we propose a gradient descent-based method to solve this optimization problem. So the natural question here is how can we reverse engineering the backdoor trigger TB given the bug instance containing the backdoor image? So our solution is resort to interpretation machine learning method. So we define an objective function which formulates the dissimilarity between the misclassified input and reference input. And we use the interpretation machine learning method to compute attribution score for each pixel in the backdoor input. And we can use a clustering to cluster it into 2 clusters. First cluster contains all non-trigger pixels. The other one is trigger pixels. The trigger pixels cluster will have higher attribution score contribute to the objective function. So in our experiments, we consider backdoor encoder as the backdoor method. And we use Sinclair as pre-training algorithm. And we use 2 different pre-training datasets. And when building a downstream classifier, we consider 3 benchmark image datasets. And we consider a fully connected neural network with 1 hidden layer as the downstream classifier. And in our paper, we also consider language foundation models and vision language multimodal foundation models. And more results can be found in our paper. Regarding the setting of Mudjacking, we randomly select 1 bug instance from the testing set in the dataset. And we set the weight of locality loss and generalizability loss equal to the weight of effectiveness loss. And we randomly, we train the patching process for 200 epochs. And we randomly select 50,000 images as the validation data. And for evaluation metrics, we aim to measure whether we achieve the 3 patching goals. So in order to measure the effectiveness goal, we use the correct prediction for the backdoor input. So basically, if the downstream classifier makes wrong prediction, it's misclassified. If it's correctly predicted, it's we mention its correct prediction. And in order to measure locality goal, we measure the testing accuracy of downstream classifiers built on top of foundation models. It's a fraction of correctly classified clean testing examples. And to measure the generalizability goal, we use 2 metrics. The first one is attack success rate. So if an attacker's target class is truck, if the downstream classifier successfully output attacker desired label, we call attack success. Otherwise, it fails. So attack success rate measures the fraction of success. And we also use accuracy of backdoor triggers. So it's a fraction of correctly classified backdoor testing examples embedded with a trigger. So regarding our results, Mudjacking achieve all 3 patching goals. So before patching, we find that downstream classifier will make wrong prediction, and the accuracy are relatively high, and attack success rate are almost close to 100%, with accuracy of backdoor images close to 0. So basically, it will make wrong predictions for any input embedded with a trigger. But after patching, we find that we can achieve the effectiveness goal by correctly predict the label for the backdoor image. And also, we maintain the accuracy to achieve the locality goal to make the foundation model still useful, but free of backdoors. And the attack success rate are degraded a lot and close to 0, which means it's almost free of backdoor. and accuracy B is close to original accuracy after the patching. So it's like now will not impact much as the backdoor foundation model. And our results also generalize to different data sets and also different modalities. We do want to mention that people may come up with like different adaptive attacks. So given different shapes and patterns of trigger, our default setting is a white patch here. And we may consider random pixels, right? We can randomly construct a backdoor trigger to have different patterns. And our method still achieve the 3 patching goals. And we can even with different shapes, right? Like the triangle here. And we can even consider the real world examples as backdoor trigger, like the Apple logo here. As long as you taking an image with the iPhone logo, it will make a wrong prediction. But our method can still patch such backdoors. And also like the smile sticker here. So besides this single trigger, we also consider combination trigger that 2 triggers can be exist in the same input. So it will take effect as long as 2 triggers exist together. But our method can still achieving the 3 patching goals in this setting. And lastly, I want to mention that our method is general enough, not only patching backdoor vulnerabilities, but also can patch normal bug. So what do we mean by normal bug? We mean it's normal misclassification error. Basically, an image was misclassified, and then we consider it's a normal bug. So there is no generalizability goal here anymore because it's not backdoor attack. But our method can still make correct prediction for the misclassified input and maintain the utility. So as come to the conclusion, we want to mention that we propose Mudjacking to patch a foundation model's backdoor vulnerability without sacrificing its utility. And also our method can patch normal misclassification errors for foundation models. Yeah, thank you. I'm happy to take any questions.